Alright, welcome to example 3. We're going to solve the given differential equation, and here we have x cubed times y triple prime plus xy prime minus 1. So it's a Cauchy-Euler because our powers with our x's match up with the order of our differentials. And so here it's x cubed y triple prime, so it's a third order differential equation. So I can't just use that nice little formula am times m minus 1 plus bm plus c. Here I actually have to, substitute in and find. And so again, we're saying that y is equal to x to the m, and so our derivative of that was just m times x to the m minus 1. Our second derivative would have been m minus 1 times m times x to the m minus 2. And then our third derivative is just m minus 2 times m minus 1 times m times x to the m minus 3. And so that's our third derivative. And now what we're going to do is we're going to actually substitute in and find it. So I have x cubed times all of this. So it's going to be m minus 2 times m minus 1 times m times x to the m minus 3. And again, x cubed and that minus 3 with the x right there are going to cancel out. Plus x times y prime, which is just m x to the m minus 1, which again, that x and that minus 1 is going to cancel each other out, minus y, which is just x to the m, and that's set equal to 0. And now, what we're going to do, we're going to pull out all of our x to the m's, we're going to cancel some stuff out. And so, what I see here is I'm going to have m minus 2 times m minus 1 times m. Let me go ahead and write, we're okay, plus, I'm pulling that x and that minus 1 cancel each other out, and I'm going to pull out that x to the m, so just plus m minus 1, and have x to the m equals 0. Again, notice I didn't write my x cubes because x cubed and that x to the m minus 3, that minus 3 and that x with that x cubed, they're going to cancel each other out. Same thing with that x and that minus 1 with that x. Then I just pulled out x to the m, and now I'm going to go ahead and multiply. M times m is m squared times m is m cubed. M times negative 1 is negative 1m. Negative 2 times m is just negative 2m. So negative 1 m minus 2m is minus 3m times m is minus 3m squared. I'm sorry, that could have been confusing. Negative 2 times negative 1 is just positive 2 times m, so plus 2m plus m minus 1 equals 0. Combine my like terms, m cubed minus 3m squared plus 3m minus 1 equals 0. So now we have a polynomial of the third degree. So if we want to factor this, we got, 4 terms. We really can't group the first two and the last two. And so what we want to do is we can do our p's and q's. The good thing about this is our leading coefficient's 1 and our last term is 1. It's a negative 1. So I would try synthetic division with 1. When I do that, it's going to work. And so then I'll have something left over. So just when I factor this, I'm going to get m minus 1 cubed, and that equals 0. And so here, what I realize is that I'll have repeated roots, not once but twice, because m sub 1 is going to be 1, but so is m sub 2, and so is m sub 3. And so that means that, when I write my solution, it's going to be y equals c sub 1 x to the m sub 1, which is 1. I didn't have to show it, but there's the 1. plus c sub 2 x to the first power, I'll just show it since I showed it there, times natural log of x plus c sub 3 times x to the first power. So they're all to the same power, but they're going to multiply. This one's going to multiply by natural log of x squared. And there's the solution. So it's not bad when you have repeated roots. Now, the last case is there's the conjugate complex roots case, and it's very similar to when we were doing the auxiliary equation back in section 4.3, when we have complex roots, where we're going to get our m is equal to some alpha plus or minus beta times our imaginary I. And if that's the case, when this happens with the Cauchy-Euler equation, instead of proving, how we're going to find the solution, again, if you'd like to see that, I'll go ahead and write that up for you. But it's pretty long, and to save, some time in these videos, what our solution will be is very similar to our last solution. Instead of e to the alpha, it's going to be x to the alpha times c sub 1 cosine, and then instead of beta x, it's going to be beta natural log of x. And then our second solution is going to be plus c sub 2 sine of beta times natural log of x. And that's what our solution is going to be for conjugate complex roots. So when we write our auxiliary equation and we find that our m is going to give us, some complex numbers, so our roots are going to be complex, this is what our solution should look like. And so this is what we're going to reference back to when we're solving differential equations that look like a Cauchy-Euler equation that we get complex roots. So let's look at an example there.